Okay, let's dive in. So we use these large language models now pretty much daily, right? For emails, brainstorming, all sorts of things. And they are amazing, no doubt. But have you ever hit that point where maybe you're working with a really long document or you come back to a conversation later and the models just seems to have forgotten everything?
Yeah, that's a really common experience, and it stems from a pretty fundamental aspect of how they currently work. They operate within what's called a context window.
Right, the context window.
Think of it like a digital notepad with a fixed number of lines. As new information comes in at the top, the oldest stuff at the bottom just scrolls off and is, well, effectively gone from the model's immediate attention.
And just making that notepad massively bigger isn't really the answer, is it?
Not easily. It gets computationally very expensive, very fast. It scales poorly.
Exactly. So that's why they go with, say, understanding a whole novel or keeping track of a complex project over days. That memory is just tied to that limited window. But what if we could change that? What if we could give them a way to have scalable long-term memory, something that lets them reach back way beyond that small window?
Well, that's precisely the big idea behind the research we're digging into today. It's a paper titled M plus M, Extending Memory LLM with Scalable Long-Term Memory. It was presented at ICML, the big machine learning conference. We've got the paper itself and some really helpful research notes from the authors.
Okay, so our mission today, sticking strictly to these sources, is to unpack M plus M. What is it technically? What are the key innovations that give it this long-term recall? And crucially, what do the experiments tell us about how well it works and what it might mean?
Right. And to really get why M plus is interesting, it helps to quickly look at how people have tried to tackle this memory problem before, because just brute forcing a bigger context window is, like we said, tough.
Yeah, the sources mention sort of two main strategies for giving models external memory beyond the basic context window.
Exactly. The first one is what they call token level memory. This is maybe the most straightforward idea. You store memory as actual text.
Like generating summaries of past conversations or maybe connecting the LLM to an external database.
Precisely that kind of thing. Systems like MenGPT or ChatDB, which the notes mention, fall into this bucket. The upside is it's interpretable. You can literally read the memory. And it can be flexible. But the downsides, as the paper points out, are that storing raw text can be inefficient, lots of redundancy, and it can be hard for the model to smoothly integrate or resolve conflicts between different bits of stored text.
Okay, so that's storing readable text. What's the alternative?
The other main approach is latent space memory, and this is where M plus fits in. Instead of text, memory is stored as high dimensional vectors. Think of them as the model's internal, compressed representations, the hidden states.
So less like sentences and more like abstract numerical patterns, concepts encoded in numbers.
That's a good way to put it, yeah. The big advantage here, highlighted in the research, is compression efficiency. These vectors pack a lot of information densely. Plus, you can potentially train the memory system end to end with the main LLM, so it's more deeply integrated.
Right, and memory LLM, which M plus builds on, was already doing this kind of latent space memory.
It was. Memory LLM was a real step forward using these layered hidden states as kind of working memory. But the M plus paper explicitly points out its limitation. While MemoryLLM worked well up to maybe 16,000 tokens, it, quote, struggles to retain knowledge beyond 20K tokens.
Okay, so M plus is specifically designed to push way past that 20K barrier.
That's the goal.
So let's get into the nuts and bolts then. How does M plus actually achieve this? This seems to be where the core innovation lies, especially from an academic standpoint.
Absolutely. It fundamentally adds a new component and alters the memory handling process compared to MemoryLM. So MemoryLM had this memory pool across its layers, right? M plus calls this the short-term memory, or theta. In their experiments, this short-term memory holds 10,240 tokens worth of representations per layer. Think of this as the active workspace.
Okay, that's the notepad that gets filled like the standard memory LMM part.
Exactly. Now, the key innovation in M Plus is the addition of a brand new long-term memory LTM component, which they call Fat capital Theta. This is also structured layer by layer, but the crucial difference is its size is flexible and much, much larger. They tested up to 150,000 tokens.
Wow. Okay, so a small active workspace STM and this massive flexible archive LTM. How do they talk to each other? What's the process?
This is the second big innovation, the update process. In the original memory at LLM, when that short-term memory was full and you needed to add new information, the oldest K tokens, 2,560 in their setup, were just dropped.
Just discarded, forgotten.
Gone, exactly. M plus's crucial change here is that instead of discarding those K oldest tokens from the short-term memory, their latent vector representations are moved into the long-term memory for that layer.
Ah, so they're not forgotten, they're archived into this bigger storage.
Precisely, they're retained. The sources also mention these archive tokens get an age marker, so the LTM maintains some chronological order too.
That makes sense. So you're building up this large history in the LTM. How does the model then use that history when it needs it, like during generation?
That's the other side of the coin, the generation process. When M plus is generating new text, it doesn't just look at the short-term memory, it actively retrieves relevant information from that much larger long-term memory.
Okay, retrieval. How does that mechanism work? How does it find the right stuff in that potentially huge LTM?
They designed and co-trained a dedicated retriever module for this. For each layer, this retriever's job is to search through that layer's LTM pool and find the K0 most relevant tokens, that's 2,560 in the experiments.
Finds the 2,560 most relevant old tokens from the LTM.
Yes, based on the current processing state. And then these retrieved LTO tokens are effectively concatenated or combined with the current short-term memory tokens, the 10,240.
Got it. So when the model is deciding the next word, its attention mechanism isn't just looking at the 10K recent tokens, it's looking at a combined set of 10K recent plus 2.5K relevant old tokens. So 12,800 total tokens feeding into the cross attention.
Exactly that. It dynamically pulls in relevant history from the LTM and merges it with the immediate context in the STM. That combined memory view is what the model actually uses to generate.
That retriever sounds absolutely critical then. Is there anything particularly novel about its design or how they train it? That feels like a key academic contribution.
It is. The paper emphasizes its efficiency. They contrast it with some other methods like SnapKV or H2O, which might need to perform retrieval calculations for every single attention head in every layer. That gets computationally heavy and adds latency.
Right, that sounds like it wouldn't scale well linearly.
Exactly. M plus's retriever, however, operates just once per layer, serving all the attention heads in that layer. It uses two small neural networks perceptrons, one FQ to create a query from the current state, and another FK to create keys for the memory vectors stored in the LTM. This once per layer retrieval, working on the compressed hidden states rather than complex key value pairs to head, is a significant innovation for efficiency and scalability.
And how does it learn what's relevant? How is it trained?
Through a compressive objective function. Basically, during training, the retriever is rewarded for making the query representation close to the key vectors of memory tokens that are actually useful, relevant, for the current task, and far from the keys of irrelevant memory tokens. This joint training makes the retriever really good at pinpointing the most helpful snippets from that vast LTM, specifically tailored to work with these latent representations. That's definitely a core piece of the academic novelty.
That efficiency point once per layer, using compressed states, seems really important for making this practical at scale.
Definitely. The whole design seems geared towards scalability.
The notes also mention something called a multi-LoRa design. How does that fit in?
Yeah, that's another interesting detail in their setup. They use two separate sets of LoRa adapters. These are small, trainable modules added to the main model.
Two sets. Why?
One set of LoRa weights is active during the update phase when the model is processing input and potentially writing information to the LTM. The other set is active during the generation phase when the model is reading from the LTM via the retriever and producing output.
Huh. So like specialized tools for writing to memory versus reading from memory.
That seems to be the underlying idea. The authors suggest drawing a parallel perhaps to encoder-decoder models like T5, that this separation might make learning easier for our model. It could help disentangle the complex tasks of efficiently storing information versus efficiently retrieving and using it. It's a subtle but potentially important part of their training strategy.
Okay, this sounds like a pretty sophisticated system to build and train. I assume the training process reflects that complexity.
Oh, absolutely. They detail a very specific multi-stage training curriculum using Llama 3.1-8B as the base model.
What's the first stage?
Stage 1 is continual training of MemoryLLM. They start with the base Llama 3.1-8B, add the short-term memory structure, set to 12,800 tokens initially for this stage, and train it on a big data set of relatively short documents like FineWeb EDU. This just gets the model comfortable using the basic memory structure on standard texts.
Building a foundation. Then they move to longer stuff.
Exactly. Stage 2 is long context modeling. Here, they shift the training data to much longer documents sourced from Slum Pajama, with lengths going up to 64,000 tokens. They specifically mention upsampling the longer documents. The key here is that the long-term memory and the retriever are not active yet. This stage is purely about adapting the model to process extended sequences and understand long-range dependencies, preparing it for the next step.
Okay, getting it ready. And then stage 3 is where the magic happens.
Pretty much. Stage 3 is training with long-term memory. They take the model from stage 2, and now they finally activate the full M plus system, the long-term memory, and the co-trained retriever. They use a new dataset of long documents specifically crafted so the model has to learn to use the LTM effectively. This is where it figures out how to retrieve relevant history and integrate it properly with the short-term context for generation.
Wow. Yeah, that's a really carefully staged process. You could see why just throwing it all together at once might not work.
Right. That structured curriculum seems essential for training such a complex memory system.
Okay, the technical design sounds really innovative, especially the LTM and the efficient retriever. But, the proof is in the pudding. How did M Plus actually perform in their experiments?
The results they report are pretty compelling, especially on the tasks designed to stress long-term recall and understanding. For long context understanding, using benchmarks like Longbook QA and a new one they introduced, Longbook Event QA, M plus, quote, consistently outperforms all baselines they tested against.
All of them, including like standard llama models with big context windows.
Yes, including Llama 3.1 variants with larger static context, another retrieval method called SnapKV, and even a traditional keyword-based retrieval like BN25. The paper points to M Plus's superior QA F1 scores and highlights its ability to excel at identifying ground truth events. This really shows it can track and reason about information spread across very long documents, dependencies that other models miss.
And it's doing this better reasoning while only actively attending to that, what was it, 12,800 tokens per layer?
That's right, 10,240 from STM, plus 2,560 retrieved from LTM, plus the generation window itself. It strongly suggests that for truly long-range tasks, this kind of smart memory architecture beats just making the static window huge.
Okay, that's understanding. What about the absolute core goal, just plain knowledge retention over long spans?
That's where the results are perhaps most striking. On knowledge retention benchmarks using datasets like Squad and Natural QA, M Plus shows a huge improvement over the original memory LLM 7B it builds upon. And importantly, it significantly surpasses Llama 3.18B equipped with SnapKV.
How much better? What's the key number?
The headline figure from the paper is that M Plus extends effective knowledge retention from under 20K to over 160K tokens. That's compared to SnapKV, the main competitor they tested in this latent-space category, which apparently started to struggle beyond just 30K tokens.
Wow, 20K to over 160K. That's an eightfold increase in the span it can reliably pull information from. That is genuinely long term.
It's a massive leap. Yeah, 160,000 tokens gets you into the territory of very long reports, books, extensive logs.
Okay, impressive performance. But what about the practical side? Long context models usually gobble up GPU memory. How does M plus fare there?
This is another strong point highlighted in the paper. They really focused on GPU memory efficiency. M Plus apparently has the lowest GPU memory cost except for Llama 3.1-8B 16K, which is a smaller context baseline.
How does it achieve that, especially with that massive LTM?
The crucial technique here is CPU offloading for the long-term memory vectors. Instead of storing all those fifth vectors, potentially 150K tokens worth per layer, in the expensive GPU VRAM, they keep them in the much larger, cheaper system RAM, CPU memory.
Ah, so they're not sitting on the GPU unless needed.
Exactly. They're only transferred to the GPU briefly, layer by layer, right when the retriever needs to access them for that layer's computation. Then they can be discarded from the GPU memory.
Does that add much delay moving data back and forth?
It adds a little latency, yes, but the benefit is huge for the GPU memory footprint. The LTM mechanism itself doesn't increase GPU cost over the base memory LLM structure. And with this CPU offloading, M Plus actually becomes the most GPU memory efficient model they tested for handling very long contexts.
That's huge for deployment, right? Making these powerful long context models accessible without needing absolute top-tier GPU clusters.
It's a very practical consideration, yes.
But it's not universally better in all situations, is it? The paper mentioned a trade-off on shorter documents.
That's true, and they're upfront about it. On the long bench evaluation suite, when looking specifically at tasks with shorter input documents, around 8K or 16K tokens, M Plus generally performed on par with the standard Llama 3.1-8B baseline on most tasks. However, on a couple of specific datasets like Hot Potka and Musique, it actually performed slightly worse.
Any idea why that might be?
The authors offer a couple of reasons rooted in M Plus's design choices, which prioritize scaling to very long contexts. First, that mechanism where older tokens are dropped from the FTM and moved to the LTM FI. While essential for linear scaling, it means some information leaves the immediate attention window sooner than in a model with a fixed, larger window that keeps everything until it's full. So, minor info loss is possible.
Okay, a consequence of the archiving process.
Right. Second, M+'s attention mechanism is optimized for linear scaling over potentially hundreds of thousands of tokens. This differs from models designed for, say, up to 32K tokens, which might use full quadratic attention across that entire shorter context. M+'s approach might be less optimal for squeezing every last bit of performance out of relatively shorter texts.
So it's a classic engineering trade-off. They optimize M plus for exceptional performance and scalability at 100K plus tokens, accepting a small potential dip compared to specialized, shorter context models in the 20K range.
That seems to be exactly the situation. It's a design focused on breaking the long context barrier.
Makes sense. The paper also included some analysis, kind of looking under the hood.
Yes, some interesting bits there. They checked model quality on standard short context tasks, like predicting the next word within 2048 tokens, and found Plus's perplexity was very close to the base Llama-3.1-8b. So adding the memory system didn't really hurt its fundamental language modeling ability.
Good sign. And did they verify the retrieval quality? Does that retriever actually pull useful stuff from the LTM?
They did. On those knowledge retention tasks, they found the retriever successfully pulled about 30% of the actual ground truth tokens needed to answer the question from the LTM, compared to just randomly grabbing tokens from the LTM, which would only get about 3%. That shows the co-trained retriever is genuinely effective at finding relevant history.
Okay, 30% sounds pretty good. What about speed and compute latency in FOPS?
They confirmed M+'s processing time, latency, scales roughly linearly with the sequence length, which is the goal, avoiding that quadratic blowup of standard attention. Adding the memory and retrieval does add some overhead compared to the base model, naturally. But crucially, with the CPU offloading enabled, the extra latency cost at a very long input length, like 128K tokens, was only around 3%.
Only 3% extra time for all that memory access at 128K. That's pretty efficient.
It seems quite manageable, and in terms of FLOPS, floating point operations, a measure of computation, M plus and the baseline Llama 3.1-8b were comparable per generated token. The bigger story wasn't raw FLOPS, but feasibility. At 128K tokens, the standard Llama model ran out of memory in their tests while M plus kept working. That really underscores its superior scalability at functions where others simply can't.
And they even looked at the memory vector interpretability. What did they find there?
Yeah, they did some analysis suggesting the vectors stored in the LTM behave similarly to normal transformer hidden states. Lower layers capture more surface-level text features, while higher layers capture more abstract semantic meaning. So the LTM essentially functions as this large, layered cache for the model's semantic understanding over time.
Okay, so pulling it all together, M plus really does seem like a significant technical advance for LLM memory.
I think that's fair to say based on their results. By adding that scalable long-term memory component and pairing it with the efficient, jointly trained retriever, they've demonstrably pushed the boundaries of knowledge retention well beyond what MemoryLLM or other methods tested could achieve, getting reliable recall out to over 100 tokens.
And critically, they managed this while keeping GPU memory usage highly efficient, especially with the CPU offloading truck. That makes it feel much more practical.
Definitely, that practical efficiency combined with the performance leap is a key takeaway.
And the authors noted their immediate next step is to work on optimizing that CPU-GPU data transfer to reduce the latency from offloading even further.
Makes sense. If you can shave down that 3% overhead, it becomes even more appealing.
So thinking bigger picture, what kind of potential positive impacts could this scalable memory unlock? Where do the authors see this going?
They suggest benefits across a range of fields: education, research, industry. You could imagine an AI tutor that actually remembers your entire course history, or a research assistant that can truly internalize and synthesize information from dozens of long papers, or an industrial system that understands the full operational context from years of logs. It's really about enabling LLMs to retain and retrieve long-term information more effectively, making them more powerful partners for complex, knowledge-intensive human tasks.
That really does sound potentially transformative. But, as always with powerful AI advances, there are potential downsides and risks. The authors themselves flag some important concerns in the paper, don't they?
They do, and it's really important to highlight that. In their ethics and impact statement, they explicitly raise concerns around AI safety, reliability, and fairness. They point out that a model with such powerful long-term memory could, for instance, propagate biased content over extended text spans.
Meaning, if there was bias hidden deep within a massive document it ingested, it could keep recalling and potentially amplifying that bias.
Exactly. Other concern they raise is that it could store sensitive information for unintended durations. If personal data gets into that long-term memory, its persistence becomes a much bigger privacy issue.
Right. So the very capability that makes it powerful long-term retention also creates new risks if not managed carefully.
Precisely. The authors stress that deploying systems with this kind of capability requires robust safeguards, including bias mitigation strategies and ongoing oversight. The technical progress needs careful ethical consideration alongside it.
It really underscores that building smarter AI isn't just a technical challenge, but a socio-technical one.
Yeah.
So maybe here's a final thought for you, the listener, to chew on. Really think about what it means if an AI can genuinely remember, not just in a short window, but across vast amounts of information, entire conversations, whole books, long histories. How does that fundamentally change the kinds of interactions you could have, the tasks you could delegate? And perhaps more importantly, what new questions does that raise about trust, about control, about privacy, and about the responsible path forward in developing and using these increasingly capable systems?